period. Let's go to I believe this is our final definition of the unit, which is radiometric dating. So we're going to determine the age of rock based on the amount of radioactive decay in the rock. And we're going to compare the amount of parent material to daughter material. I'm not going to lie, this is one of the most difficult concepts to understand, I think, in the entire unit. I'm going to try my best to explain it to you. When we look over here, we have an unstable isotope. When we add up the protons and the neutrons, we get a number which is 14 over here. And all we know is that matter cannot be created nor destroyed. It has to stay that number totally. So even though it goes through a change of radioactive decay, when it ends, it's now stable. It's stable because it has the same amount of protons and neutrons, but that number equals that number over there. By the way, if you're getting freaked out right now, like I didn't understand a word of that, don't worry. You don't need to understand what an unstable isotope is and a stable isotope is yet. What you do need to know is that over time inside of rock, it goes through this process called radioactive decay. And through this process, we can learn how old a rock is. That's all you need to know, is that by scientists looking at this process taking place, they can figure out exactly how old a rock is. Not using relative dating, saying, oh, this rock's older than that rock, but exactly how old it would be. So here's one way we're going to try to do this, okay? We're going to try to do a math problem. We're going to try to figure this out. I believe in you to be able to figure this out over here. So what is parent material? Parent material is the stuff that comes first, right? A parent would be around before the daughter would, has to be. So it says after every half-life, the amount of parent material decreases by 1/2. So here is a brand new rock, right over here, brand new. Okay, it was created, just newly formed igneous rock, let's say. It is right now 100% parent material. You can see 16 out of 16 of it, or 100%, is parent material. Now, after one half-life, it has gone through 50% shift over here to daughter material. So it's 1/2 parent material, 1/2 daughter material. After another half-life, it goes through 1/2 of 1/2 is now 1/4. Okay, so that means that 2 half-lives have happened, and 1/4 of the original parent material, which is red, is left over. And then after another half-life, half of 1/4 is 1/8, and then you only get 2 out of the original 16. If you do it again, it would be 1 out of 16 that is left. If you did it again, it would be 1 out of 32. You just have to cut all these in half over there. Let's try to figure out this chart over here. It's actually easier, I believe, if you go in reverse order, believe it or not. So let's look at this one. Parent material left is 1/4. The half-life is 10,000 years. So what's the age of this rock? Okay, well, we know this is the original amount, and this means that there's 2 half-lives. If the half-life is 10,000 years old, that means this is 10,000. And then to get here, it would be another 10,000. 10,000 plus 10,000 is 20,000. That number would go right there. So this is a 20,000-year-old rock. That's how we just learned the age of this particular rock right here, by looking at the parent material and comparing it to the total amount. Okay, let's try the next one over here. The half-life we now know is 1.3 billion. So each time it goes here, 1.3 billion plus 1.3 billion plus another one. And the current age of the rock is 3.9 billion. So what amount of parent material is left? Well, we can divide this number by this number. 3.9 divided by 1.3. And that means that there would be 3 half-lives that took place, right? So this would be 1.3 billion, this would be 2.6 billion, and this would be 3.9 billion. That means that there were 3 half-lives, and we would get this fraction of the original parent material, which goes right there. Can you figure out the last one? The original parent material is 1/8. However, this time the age in years is 30,000. So this is a 30,000-year-old rock. It's not 3.9 billion in this particular example. So if it's 30,000 years old, and there have been 1, 2, 3 half-lives, then how much is each half-life if the total age is 30,000? We take 30,000, we divide it by 3, and each one is worth 10,000. Were you able to follow any of that? I hope you were. I'm trying my best to make it make sense to you, but I know it's tricky. Let's go through here. We have more questions to try and figure out radiometric dating in more detail. What does the y-axis represent in this? We always want to be able to look at a chart and quickly be able to ascertain what's the most important piece of information on here. right? We know this is an XY graph. This is the x-axis, and this is the y-axis over here. So the y-axis is the percentage of original isotope remaining. This means that a brand new rock that was just formed right here, it is 0 years old, it's 0 half-lives has occurred. It has 100% of its original parent material. What percentage of parent material is there after 0 half-lives? The answer is 100 right there. So far, so good? Well, what about at 1 half-life? What percentage of original parent material is left? Well, we go to 1, we go straight up over here, and it tells us that 50% would be left. So that would be right there. Pause it and see if you can do the rest of them. What about after 3 half-lives over here? It's a little hard to tell what the exact number would be, but it's about 12.5% right there. The reason I really know that is because I just keep dividing this number in half. 100 divided in half is 50. 50 divided in half is 25. 25 divided in half is 12.5. 12 and 5 tenths. Okay, look at the half-lives of 7 and 8. Now they're really similar to each other. Which one has more parent material left? We don't even need to know what these numbers are exactly. We could figure them out. We could take 12.5 and divide that in half, and then divide that in half, and divide that in half. But we also know that as time goes on, we just keep dividing in half. The number is always going to get smaller as we go to the right. So if 8 is smaller than 7, 7 has more parent material left than 8. 6 has more than that. 5 has more than that. Between which two half-lives is there the largest decrease? So between this and this, or this and this, or this and this, which two of them does the number decrease or go down the most? The answer is between 0 and 1, right? It goes down from 100 to 50. That's a decrease of 50. If it went down from 50 to 25, that's a decrease of 25. So this is the largest decrease. That means, of course, that the smallest decrease would happen over here. We don't know what the exact number is. We don't have to know, but we just know that these would be the closest to each other because you see how they're gradually the gap is getting smaller and smaller between them. Hopefully, as confusing as this chart wasn't too confusing for you. This is going to lead us back to our original phenomenon. We know so much more now than we did before. Let's see if we can figure out the answer to this phenomenon. How is it possible that fish fossils were found at the top of Mount Everest? Okay, well, we know the process of fossilization, right? A creature had to die, get buried pretty quickly, and then over time, it had to get filled in with groundwater. So once upon a time, this part over here was not at the top over here. It had to be underwater. That means that this mountain didn't exist. There was a time when this fish existed that preceded this mountain existing. So we know that the tectonic plates are currently in motion. We learned that in the last unit. So although Mount Everest is the tallest point today, once upon a time, it was not only flat, but it was underwater. And it was underwater where fish could exist above it. So the fish fell down to the bottom of the ocean at some point, and it was buried underneath there. It became sedimentary rock. We know only sedimentary rock would keep fossils there. And it survived being pushed up together until the tectonic plates crashed together, pushing this entire mountain up over time, pushing it up, pushing up, pushing up. But this part never fully eroded away, or eroded away just the outside for us to still find. Could be microscopic fish that are up there or fish up there. But even so, there are fish that were found in the Himalayan mountains, which I just think is an absolutely wild phenomenon that now hopefully you would be able to discuss. Right? Creature existed a really long time ago, before the mountain existed. The mountain got pushed up because tectonic plates came together to push up. This would be a convergent boundary pushing it up. But this used to be underwater a really long time ago. And now it's at the top of Mount Everest near India.